All right, so hopefully you got some answers to these, and hopefully your answers are correct. But so if we look at the first one, the derivative of f of x, well, the 5 stays there because it's a constant times 2 to the x. So the 2 again drops down in front, and the 2 turns into a 1, plus 3 because it's a constant times the 4 drops down. X to the 4 minus 1 is 3. So this becomes 10x plus 12x cubed. And g prime of x, the derivative of g, similarly, we have 2 because it's a constant times 7 because the 7 drops down. 7 minus 1 is 6 minus 3 times 4 times x to the 4 minus 1 is 3. So this equals 14x to the 6th minus 12x cubed. All right, we're going to do one more problem, but before we do the problem, just a reminder of some of our first and second derivative rules. And this is stuff that we were looking at in the first unit of our Moodle or the second chapter of the BEST calculus book. And by best, I mean George Best, but also best because it's the best. Okay, so anyway, here are some things that we remember. If the first derivative is 0, our function is increasing. If the first derivative is negative, the first derivative, our function is decreasing. And if the second derivative is positive, f prime is increasing and f is concave up. And if the second derivative is negative, the first derivative is decreasing and the function is concave down. We remember that. We know that. And if we don't know that, know this. So know this, learn this, commit it to your memory. If you're not sure how, go back and watch videos, come and talk to me, talk to your peers, talk to friends, talk to anyone, but make sure that you learn this. Because once you know this, you will be happy. Okay, so considering this information, we want to answer this question. It says find and interpret graphically the second derivative of f of x. Well, we need to take the first derivative first, and the first derivative will be 3x squared minus 3 times 2x, which is 3x squared minus 6x. That's the first derivative. The second derivative, we take the derivative of the derivative. So that's going to be 3 times 2x to the 1 minus 6, which is 6x minus 6. And we know what this looks like. It says find and interpret graphically. So this is a linear function that has a y-intercept of -6. When x equals 1, it's going to go through the x-axis. So it's a graph that looks like that. Here's the point 1 comma 0. And find and interpret the second derivative. Well, what does that mean? It means for x less than 1, f is concave down. And we know that because for x less than 1, my second derivative is less than 0. And x equals 1, I've got a point of inflection. And for x greater than 1, I know that f is concave up. So by taking the derivative and then the second derivative, I can very quickly and easily see some attributes of the function itself by looking at when my second derivative, when is f, let's try that again, when is f double prime less than 0, and when is it greater than 0. And by looking at those things, I can determine concavity of my original function. So that's it. What we did today, just to kind of go back to the main page, is develop some important rules. Here they are. We started off with the limit definition of derivative, but now we've extended that to some rules where we don't have to use this anymore. No more in certain cases. For example, if I have a function that's a constant, the derivative is 0. If the function is a linear equation, the derivative is just the slope. If it's a power function, then we use this constant multiple rule. The constant goes in front, and then we just take a derivative of the function, and that over addition and subtraction, differentiation can be distributed. Okay, that's it.